So the first thing we're going to talk about is time-harmonic fields. This is converting the wave equation into the frequency domain using phasor notation. So phasors, we encountered phasors in transmission line, and before this class, we also have experience of phasors. Basically, if you have some function of space and time, then we can use a mathematical skill called separation of variables. So we can separate the time dependence and the spatial dependence into different parts. So this is basically phasor notation. We want to explicitly write the time domain dependence, j omega t, out as an independent part. And only the spatial part is the one to be solved. And this also means we have to assume we know the operating frequency. Exponential j omega t, so you have the time dependence, but you also have a designated frequency. Alright? So once we write this function of space and time in this form using separation of variables, whenever we have temporal derivative, it's only operating on this exponential j omega t term. This term is only spatial dependent. Okay? So this term, called the phasor term, does not participate into the time domain derivative. It's only this one. As a result, whenever we have a time domain derivative, we have j omega multiplied in the front. This is not something you don't know. We already covered that in transmission line. Voltage and current waves, we can express it using the phasor notation multiplied by the time dependence. Okay. So now, as we move into the vector fields, E fields and magnetic fields are vectors. Voltage and current are scalar quantities. But vector fields can also be expressed using phasor notation. So basically, phasor is only having the spatial dependence and then multiplied by the time dependence. Okay? So now let's take a look again at Maxwell's equations under the strong assumption of simple medium, linear, homogeneous, and isotropic medium, and also source-free and current-free. So what we're trying to remove or simplify is we don't really like to have this time derivatives, okay, in the Faraday's law and the modified unpaired circular law. So we now use phasor notations for E fields and H field. Okay. So the first equation written in the phasor notation now reads curl of E is equal to negative j omega multiplied by mu h. Right? We're only replacing the fields with phasors, so now whenever we have a temporal derivative, we have a multiplication of j omega. The Gauss's law does not change, but this one does. This is the modified unpaired circular law. We have a time derivative, so we have a multiplication of j omega. Okay. So now we're trying to simplify these two terms, these two equations, following the same identical procedures that we used in time domain wave equation derivations. Okay, so let me just walk you through it again. This is to review the assumptions that we made. So we start from curl of E is equal to negative j omega mu h, right? We can take curl on both sides, right? So whenever we take another curl, double curl of E is equal to, this is the definition of Laplacian, vector Laplacian. Right? Again, the first term is cancelled out because we assumed we have no free charges, right? So we're only left with the negative of vector Laplacian on the E field phasor. The right-hand side is now slightly simplified, curl of the entire thing, and we can pull mu out again. This is assuming we have a very homogeneous medium. Okay? So this mu is a constant. It's not spatially dependent. But we already know what curl of H is. Curl of H is j omega epsilon E, right? So now we replace curl of H by this expression. We have j times j equals -1, and that cancels out with a negative sign, right? So we have omega squared mu epsilon E. So now on both sides, we are solving for E. So eventually, this equation is called the Helmholtz equation. It is explicitly in the frequency domain, right? You don't see the time domain variations anymore, but you see omega now explicitly. So this is dramatically different as compared to the wave equation in the time domain. In the time domain, you see this time, right, explicitly, but now you no longer have time, but you do have frequency. And this is called k squared. Okay. So these two are very, very different. In the sense, in the first one, you see time. But in the second one, you no longer see time dependence, but you see frequency dependence. Okay. So that's a major difference. This is Helmholtz equation for the E field. You can also derive the Helmholtz equation for the magnetic field. Same procedure, okay? The same procedure. So I'm not going to go into the details, but I want to highlight the result. As compared to the Helmholtz equation for the E field, the H field has the identical mathematical form, and the Laplacian is linked to itself by the same constant. So this is the point where we have to think, what type of message is delivered behind these equations? Here, if you still remember, we can replace E by H, right? For the time domain equation, right? So last Wednesday, we went over the derivation, and we obtained the conclusion that E field and H field, using the time domain wave equation, we knew that both E and H propagate with the same speed, right? That's what we have. So for E field and H field, for the first one, the time domain equation, those two equations tell us both E field and H field have the same propagation speed. But now that we derived Helmholtz equation, K is basically a spatial characteristic, right? Because we no longer have time dependence. We only have spatial dependence. So let's come back. Spatial dependence is telling us what is the periodicity of this wave in space in this given material. So that is giving us the information of wavelength. Okay, so this lambda is the effective wavelength in this given material. So we know lambda. Okay. And at the same time, E and H have the same K, so basically both E field and H field have the same spatial periodicity. That's called the wavelength, and also in the same direction. So these are the important messages behind Helmholtz equation. So now that you know, if you have the material and you have a wave propagating inside, then you would have the E field and the H field propagating in the same direction with the same speed. That means you have the same velocity, right? Velocity is a vector, so you combine those two, you have the same velocity. And these two fields have the same effective wavelength. Okay. In other words, E field and the magnetic field, they co-propagate. They propagate together. Same speed, same direction, same wavelength. Okay. So this page wants to highlight the meaning of wavelength. Okay. So we start from Helmholtz equation. Well, you might be asking, how is wavelength related to the operation of frequency? Okay. Because K is omega squared mu epsilon. Okay. So K is certainly frequency dependent, and usually our materials are non-magnetic. What does that mean? Usually mu equals to mu zero in most materials. 99% of the materials are not magnetic. Okay. But most materials are electric, meaning epsilon can be different from epsilon zero. So usually we have epsilon r. Okay. Now if you still remember multiplication of mu zero to epsilon zero and taking the square root, that is 1 over c. Okay. So let me write it down for you. So K is equal to omega mu 0 epsilon 0 and multiply by epsilon r, right? Another way to write it. But this is 1 over c. This is omega divided by c and times epsilon r. Now, starting from junior high school, you knew that the refractive index of water is 1.33. The refractive index of glass is 1.5. And that is the refractive index. Okay? So this means omega divided by c is the propagation constant K in vacuum. Okay? So this is K0 in vacuum. So if you have a wave propagating in material, an electric material, then your K is n, the refractive index, multiplied by the wave propagating in vacuum. Okay. So what does that mean? K is 2 pi over lambda. This means lambda is basically the effective lambda in certain material is the wavelength of the same wave propagating in vacuum divided by n. Okay. So we can go over it again, right? So the definition is omega of K is omega divided by your propagation speed. And your propagation speed, another way to look at it is c divided by n, right? the same thing. You can move this one to the bottom, right? So this is C divided by N. Same thing. So this means whenever you have a material, that material is trying to slow the wave down. And at the same time, it is trying to make your wavelength shorter. Okay? So the material is trying to slow the speed of the wave down by a factor of n, the refractive index, and it's also trying to reduce the wavelength by the same factor. So later today, we will come back to that. I want to give you a very clear picture how this n is coming from and how it works to slow the light down, light or wave. Okay? So I will keep those two comments on the blackboard. But usually, if you still remember, we're working in the phasor domain, meaning that we care about frequency. And in K, we see this frequency explicitly written down here. So you have to ask yourselves, where is the additional frequency dependence coming from? Well, mu 0 and epsilon 0 are really constants, but this epsilon r, the relative permittivity, usually, or let me say 100%, is frequency dependent, right? So you should add epsilon r of omega to this so-called permittivity, okay? And therefore, your refractive index is frequency dependent, okay? So later today, we are going to talk about the frequency dependence, but in a very brief sense. Okay. Now, side-by-side comparison to what we learned in the very beginning for the transmission line when we solve for the phasor equations of voltage and current. We have this result, right? And where beta is the propagation constant for a lossless transmission line. And there we also introduced beta is equal to omega square root of LC, and it is also equal to 2 pi divided by lambda. Okay? Now you compare to E fields and magnetic fields. They are basically identical, right? So the only difference is we now improved starting from scalar quantity into vector fields. Right? You might be wondering, up to now, our derivations were assuming, well, making a lot of simplifications, right? Simple material, no free charges, no free currents. Let me show you one example. If we allow the material to be conductive, meaning that you can have free current density. So J can be there. And what happens for your results? Do you need to go over the entire derivation again? Probably not, because once you allow to have J, only one equation is modified. Which one? The modified Ampere's circuit law, right? So now if you have J, you just add it back. And the benefit of using phasor notation in the frequency domain is you don't really care about the temporal duration, right? It's converted into multiplication of J omega. J, the current density, once you have the E field intensity, it's related as sigma E. Sigma is the conductivity of your material, right? So it's okay. Even though we do have the presence of free current density, it is only modifying my formulation as adding an effective term into the epsilon, right? I have two terms. They have the same E dependence, so I can gather these two terms into one, right? So this entire thing in the parenthesis, epsilon is coming from this term, and now you have added the possibility to have conductive current that is only contributing to a new term, right? We can say this is our new effective epsilon. So let me just call it epsilon C when your material is conductive. So the C represents conductive. And this is telling you, if your material is conductive, then your epsilon is no longer purely real. When you don't have the J term, right? You don't have this J term, then epsilon for typical material is purely real. But now that you do have conductive current, then epsilon, of course, is now a function of frequency, and now it is having the real part and the imaginary part. So your epsilon is now becoming a complex number. So if you think back in transmission line, we initially started assuming we do have loss, right? And then we have gamma, the complex propagation constant. And then we assumed we're working in a lossless transmission line, so that loss term is dropped, so we only have beta. So now for E fields, H fields, we're going in the reverse way. Initially, we assumed there's no loss, we only have the real part, and now we include the loss. Our epsilon is now having the real part and the imaginary part. So at this moment, try to guess what happens when epsilon is having an imaginary part. Take a look. What is happening? Eventually, you only care about negative j, k, z, the propagation. Okay? The propagation constant tells you the phase accumulated for this wave propagating in space. Now, if your epsilon is now having the real part and the imaginary part, that is making your k also complicated, right? It has the real part and the imaginary part. Now, if you compare it back to transmission line, this is gamma. Gamma equals beta minus alpha. Okay? So you have a loss. So as your wave propagates in this conductive material, its amplitude decays exponentially. Right? So that is loss. Once your epsilon is complex, the imaginary part gives rise to loss. Okay. So again, everything should be frequency dependent because we're working in the using Phasor notation in the frequency. Right? When this loss term, or the imaginary part, well, it is frequency dependent, right? Explicitly, it is inversely proportional to frequency. So that means for the same material, when your wave is of a low frequency, it behaves like a conductor. Frequency low, frequency very low, this term is very huge. Okay? And when your wave frequency is very high, a very large omega is making this effectively zero. So the behavior of that material will be more like a dielectric.